basically is preserved, and you end up getting something that is more symmetric. So you have star formation going on early, it dies out because you're using all of the gas to form the stars early, and you end up basically with galaxies like our own Milky Way, in which there's not much star formation, and space really is fairly empty. Not so in these early galaxies, shortly after the Big Bang. Then you have this symmetry. So I should say, you may wonder, why is it that you have this diagonal distribution? And the answer is that there are galaxies here, but they're too faint for us to detect. Realize we're plotting luminosity here, that is intrinsic brightness. Well, the further back in time you're looking means the further away they are, so the fainter they are. And so this line basically represents a detection limit, and we simply can't see galaxies here, but presumably there are lots of them. Here, there are no galaxies because our field is so small that luminous galaxies are not very common, and so our field of view was not large enough to see any of such galaxies. So presumably there are galaxies up here also. So this is what we call a bias or a selection effect. But the fact is, here we have the evolution of galaxies. Starting off, and this is a blow-up of these galaxies with these dysmorphic ones, and ending up here with larger, deader, because star formation has already occurred, galaxies like those that we see when we look out at relatively nearby galaxies in the local group. So, final couple of slides. And I've already mentioned that you get star formation here, but not much there. So shortly, 2 billion years, in the first couple of billion years after the Big Bang, there was lots of star formation. And then that has died down, so that we really do live in a dying universe right now. Most of the gas has been used up in stars. I want to show you 2 videos that basically look at this cosmic web calculation that I already showed you. Remember the history of the universe in 17 seconds in more detail, okay? And exactly what happens now when we take a blob like this, perform the same type of calculation, but now with our really super duper computers, can zero in on what those blobs of gas do when they interact with each other gravitationally. So the question is, we start off with this almost homogeneous gas and you get this accretion. How do the galaxies form? And the answer here is in a really neat, very sensitive touchpad here. This is a video done by Piero Medau, who was at the Institute as part of this Hubble Deep Field project, and worked on a really high-level, very advanced computer in the University of Zurich. So, starting with the hot fog, slightly inhomogeneous, you know, 1 part in 100,000, and we let it go, and you will see here a representation. I've got to get the cursor here. Promise, there's only one more slide after this. Here we go. Universe expands. It cools down, therefore it doesn't radiate, so you see it dark in the background. And here is what is happening now in more detail in these initial gas clouds that existed from the Big Bang. So with time, the merging of this material, when it happens, the angular velocity is communicated to the central object. And so you'll see here, even though the universe is expanding, the mass of the central object causes its gravity to be great enough that you produce a spiral galaxy. So we believe that, in fact, this is how spiral galaxies have been created. Kind of cool. And in fact, we believe that the black holes that are now in the centers of galaxies came from this accretion process. But that's only half of it. When we look out now, there are two types of galaxies, spirals and ellipticals. Now the question is, how do you get ellipticals? So another calculation here, if you take two spirals like this and have them gravitationally interact, here's what you get. Realize that the distance between individual stars is so great that you get almost no direct impact of individual stars, that they're all passing through each other. So the merger process, the gravitational merger process, is such that you take these two spiral galaxies and there are all these tidal effects that cause the galaxies to slowly merge together and for the two individual nuclei to become one. And that increase in mass is what produces the black holes that we now observe in the centers of most galaxies. Notice we started with two spirals, but we end up with just, we ended up with something that looked elliptical. And so this is how we believe the elliptical galaxies have formed. The spiral galaxies formed initially from these diffuse gas clouds, and the ellipticals come from the merging of spirals where you lose the spiral structure and you end up with this basically nice symmetric elliptical shape. So, this we believe is the best representation we can offer right now as to how large-scale structure has formed in the universe. Interesting stuff. To me, it is a very unifying picture because it is based on our current knowledge of physical laws, which, though incomplete as they may be, because after all, this dark energy didn't know about it more than 10 years ago, 10, 15 years ago. So there's still laws out there that we may discover. Gives us a representation of exactly how physical laws do govern the basic structure of the universe. And as someone who believes that natural processes have led to the origin of life in the universe, what I like to think is that our DNA is really stamped with the chemistry of the physical processes that have occurred in what you have just seen. And to me, that is a very unifying concept that I believe our world could use more of. Thank you very much. You've been a great audience. I'm happy to take questions. And I can't see out there. Yeah.
Yeah. So I know you talked about the expansion of space-time, but you said that the matter is not expanding, it's just space. Could you talk more about that a little bit?
Not much. And the reason I'm serious, right? One of the things you learn as a lecturer is it's very difficult to impart understanding to people if you don't understand it well yourself. So let me first say that the matter in the galaxies is gravitationally bound, and so they are not expanding. But that doesn't mean that other matter that is not gravitationally attached then isn't expanding. And so, yes, yes, that is expanding with the space that it's in. So I don't mean to say that matter isn't expanding. I mean that the matter that is gravitationally bound, either in stars or galaxies, that is not expanding, okay? So I want to make that clear. But your question really was, can I explain what is the space warp? So it is a construct of general relativity that normally light is radiation, it's electromagnetic radiation, doesn't have mass, and therefore it is not subject to gravity. But one of the results that Einstein concluded from his mathematical application trying to explain various phenomena both at high velocities and at very high mass levels was that the properties of space are such that when you have a large concentration of mass, that actually does cause the properties of space to be non-uniform. And graphically we depict that, you know, where you've got this constant grid, but if you've got mass there, then it produces a bit of a hole. And light follows what we would normally call a geodesic, that is constant energy, and so when it moves around an object with mass, it actually curves. You know, so I can make that statement, but I don't know how to give you or even myself a greater understanding of it than that, short of taking the complicated equations and being able to interpret them. And since it's not my field, I'll be honest with you and tell you that I understand the result, but not enough that